Okay, lesson 77, efficiency and power. We will explain energy conversions referencing efficiency and power. So essentially, it's just a new way to talk about energy conversion. It's just a new way to talk about energy itself. Now, I actually don't need to spend a lot of time talking about this lesson because we've already talked about both of these concepts when we talked about electricity. And in fact, the concepts are exactly the same. So this should not be necessarily a brand new lesson for you. It is a new lesson because we're applying this thing to motion, but ultimately we're applying it to energy. We've done power with regards to energy. We've looked at efficiency with regards to energy. So this should not be new. But for some of you guys, it might be weird applying those concepts to a brand new area of physics. But hopefully the more we do this, the more often you guys see this, the more often you guys are going to be like, oh, okay, I can use this formula from this part of physics and apply it to this part of physics. And that's one of the things I would really like you guys to, by the end of this year, be comfortable with, is understanding that physics is not separate units. They're all related and they're all tied together by energy. That's definitely one way you can always think about it. All right, well, before we move forward, let's take a quick look backwards. What did we do last time? Last time we were here, we looked at, and I've tried to fix these slides a little bit, but yeah, I haven't finished them yet. Motion and energy. We talked about how energy is conserved, and then we talked about this idea of gravitational potential energy. So if I take a bag and I push it up onto a higher shelf, that gives it a greater amount of gravitational potential energy. Now what that means is that it can fall. We said that the formula to calculate the gravitational potential energy is WE, the gravitational potential energy, equals mass times gravity times height. We said, what is potential energy? It is stored energy. How do you store energy? You do work against the force. So for example, if you lift a mass, if you pull two magnets apart, if you compress a spring, if you pull an elastic band, when pulling chemicals attracted to each other apart. So if you've got two chemicals that are like really, really attracted to each other and you pull them apart, you're going to create potential energy, because those molecules, those chemicals want to snap back together. And so it's not a chemistry subject, but hopefully that gives you an idea of, if you're studying in chemistry, or 11 chemistry, because I know some of you are, if you're looking at redox equations, that should give you an idea of why there is energy involved at all, because those want to come back together and you're creating potential energy. Everything has potential energy, but it depends on where you're measuring it from. And energy is relative. So for example, if we have these two mugs, we could both say that they have the same energy because there's that same part of the ground. But if one mug is falling onto a table, then we actually refer to its energy reference to the table, not reference to the ground. If it is falling towards the ground, we can calculate the kinetic energy, which is half mv squared. And then that can give us an idea of how much energy it has just before it hits the ground, when all of its kinetic energy, when all of this potential energy is kinetic energy. And I showed you this graph, which is just an idea to think about how the energy transforms over time. As the mug falls downwards, it picks up speed, and so therefore the speed energy goes up, but the potential energy goes down, but the total energy is always the same because energy is conserved. We talked about Hooke's law, which is how if you compress a spring, how much force does it require. We didn't do this example. We did this example, but I've modified it. Looking at the spring constant of a shoe, then you've got Hooke's law in a graph, and then we did potential energy of a spring, which is half k delta x squared, where delta x is the compression of the spring. Now we use X here instead of S because, I don't know, physicists are weird sometimes. And then I got you guys to work on these exercises. I put up, and then I think I got you guys to work on 11.4, yes, on Friday, I think. Yeah, I just said to do all of the questions 11.4. I know that's going to take you guys a long time, but I think it's one of the more important ideas to cover. Now, we're going to talk about efficiency, 20 minutes in, and power. So how do we talk about those two ideas? The first one we're going to talk about is efficiency. Efficiency is doing a job. Efficiency is doing a job with as little waste as possible. So that's the general definition of efficiency, and that's usually the definition that will work for an object that's for a system, for essentially people tried to work. If you're looking at like what's the most efficient way to make a car, you're looking, well, how is the way that we can make a car with as little waste as possible? With any electricity, like, well, what's the best way that we can power a house? Maybe you might have heating. What's the most efficient way to heat a house? And stuff like that. And so therefore, when we talk about without wasting as little as possible. Now, when we talk about energy, we want to look at, well, when energy is converted from one form to another, to the desired type, how much of that energy does get put in there? So we will use the symbol eta, which looks like this N, to symbolize efficiency. And the classic efficiency ratio is useful energy out over total energy in. If you want to, if you've got a, let's say you've got a heater, and you put 100 joules into that heater, and then you get something like 80 joules worth of energy out. You get 80 divided by 100 equals 80%. Now that's obviously an electricity example, not a motion example. So what would a motion example look like? And I found this picture, and I kind of really like this picture. So it's got a person throwing a ball down towards the ground. Okay. Now when she throws this, ball, it's got a EG because it's got a height. In this case, it's got a height of, and you can calculate the gravitational potential energy as 0.57 joules. Okay. Now the mass times gravity times height, and so therefore we've got that amount of energy in gravitational energy. The kinetic energy, she's throwing it toward the ground, so it's got some amount of kinetic energy, 0.46. If you add those together, 0.57 plus 0.46 gives you 1.03 joules. That's the total energy. Now you don't have to copy this down, but I thought it would be interesting to show you. The spring energy, there is no energy in it as a spring. If you go have a look at here, the total energy is still 1.03. Now it has no potential energy. All of it is kinetic. All of it is wrapped up into how fast it's going. And then it actually starts to get squashed because it hits the ground. When it hits the ground, it has no kinetic energy because it's not moving. It has no potential energy because it's not, it's on the ground, and it's got, in this case, 1.04 joules in kinetic energy. So you can sort of see that, oopsies, you can sort of see that the amount of energy is being conserved, which is exactly what we want. What we can then see is that when it bounces back up, it then gets a brand new kinetic energy. It's got a kinetic energy here of, and this is just kinetic energy, 0 total equals 0.75. Well, that's a loss. Okay. And then it bounces all the way up until all of its energy is in the form of potential energy and the gravitational potential energy here, which is going to be the same as the E total equals 0.75. So we can see that all that kinetic energy gets converted into potential energy. So we lost some energy here. And so you could talk about efficiency here. You could say, well, there's about 75 joules here, there's about 100 joules here. You could say this is about 75% efficient-ish. Now, I'm not going to go through the exact calculation here, but because I just wanted to show you guys in general what's going on here. And what it looks like is going on here is that at this red line, we're losing energy to something. And it doesn't mean that, of course, energy has to be conserved. So when we say we're losing energy, it doesn't mean that we're the energy is. It doesn't mean that that energy is disappearing. It just means it's changing. It's not going into the system to make the ball bounce. It may go towards maybe by squishing the ball, it's actually going to cause the different particles in the air inside of the tennis ball to vibrate more. And so that might cause some of the energy to be converted to heat. It might cause it to be converted to sound, to moving the air, which causes sound waves. So you can hear it bounce. I very much doubt it, but it could go towards moving the ground. Maybe you're on like some rough tiles that can be moved around easily. But yeah, ultimately you're losing some energy, and that actually makes sense. It's actually what we refer to as inelastic collision. Inelastic collision means not all energy is conserved. Well, when we say not all energy is conserved, we mean not all energy goes into bouncing that ball back up. Let's do a question. Let's do a question on this. A 230 Newton per meter spring is compressed by 5 centimeters and a metal ball is placed on it. Okay. The spring fires an 80-gram ball at 2 meters per second. What is the efficiency of the spring? So how would you do a question like this? Well, this is how I'm going to do this question. I'm going to break it into two parts. I'm going to do one part is going to be energy in, and one part is going to be energy out. So the first part, energy in, we've got a spring. So we're going to use the spring, the energy for a spring, which in this case, potential energy of a spring is half K delta X squared. In this case, it's half times 230 times 0.05 squared. Now you might be like, why did I do that? Because ultimately I can't use 5 centimeters. I've got to convert 5 centimeters into 0.05 meters. How do I convert 5 centimeters? Is by dividing by 100. And hopefully I'm praying to God that by now you guys are pretty confident at just dividing by 100, without needing to either A, put it into a calculator, or B, remember it. If you aren't, again, remember that if you divide by 100, you're just going to move that decimal point 1 twice. So that means it's going to be 0.5, so 0.05. If you divide by 1,000, you move it 1 more. And it gives you 0.005. And that's really good when you want to convert grams, which we're about to here. We're about to in the next step. So if we actually plot this out, 0.5 times 230 times 0.05 squared, 0.2875 joules. So that's how much joules is stored in the spring. So let's find out how much energy the spring gives off. So we've got an 80-gram ball, that's going to be converted into kilograms, which is going to be 0.08. Again, if you're not comfortable with that, 80 grams, you've got divided by 1,000. 1, 2, 3, 0.0, there we go, 80, 0.08. For some reason, how I do it in my head is I just cover this up and I just go, oh, that's like 80. That's how I do it in my head. I don't know, it's sort of in my mind because I just break things up into groups of 3 because that's ultimately how you do things. But yeah, anyway, so the energy out is going to be, the kinetic energy out is going to be equal to half mv squared, which is going to be a half times 0.08 times 2 squared, which is going to be 0.5 times 0.08 times 2 squared. 2 comes from here, by the way, if you're like, where is that coming from? Equals 0.16 joules. Cool. So that means our efficiency, I'm still getting used to how to write this symbol, equals energy out over energy in equals 0.16 divided by 0.2875. 0.2875. 56%. That is the efficiency of the spring. It's 56% efficient. So half of the energy, or a little bit more than half, is being converted into the motion of the pinball or the ball. Where are some of the places the system could lose energy? Can you guys give me a suggestion in chat? Where are some places the system could lose energy and how? I want some suggestions in chat for what could be the answer to this. Because I want you guys to be able to think critically. How could the system lose energy? There are 2 classic answers that I would usually always write down if you're not sure, but there are some other ones too. Where could the system lose energy? Heat is one of them. Thank you, Rochan. I'm going to make sure my volume's up in case you guys are actually speaking. Heat's one of the ones that we always do. There is possible that spring will actually, or maybe even the ball will get warm. Heat's always a classic place where we lose energy out of the system. Is there any other way that we can lose energy out of this system? Any other guesses? What's the other one that we usually say for ways that we can lose energy? Come on, guys. I know it's early in the morning, but I want you guys to participate. I want you guys to get familiar with these types of questions because I could throw this question so easily into a test. It's not funny. Sound is the other classic easy way that we could lose energy from a system. Thank you, Arben, who answered that. Yeah, sound is definitely one. If you can hear something, whenever you hear something squeak, you should be thinking to yourself, that's losing energy to sound. And it's probably not a huge amount of energy to sound, but yeah, the bulk of the energy loss that I think is going to be this. I think the bulk of the energy is going to be lost to vibrations in the spring. So if you shoot this ball, it's going to be possible for this spring to bounce forwards and backwards. And if it's still bouncing forwards and backwards, then that means that it's still got some energy, right? It's still got some bounce, it's still got some energy to it. And if it's still got energy, then that means that if it's still got energy, then that means that it hasn't passed all of its energy on, which means it's inefficient. So that's 3 of the main types. I wouldn't expect you guys to be able to get the vibrations of the spring, but that might be one. You might also have one that's like the ball spin. Maybe you could have the spin of the ball. Now you might be like, what do you mean? It's like, well, if you hit that ball on the side, you can maybe cause that ball to spin. Now, if that ball is spinning, it's still got energy. It's still got its energy in rotational movement, but that might not be something that you can record in kinetic energy. So therefore, that might be another way that you can lose energy. Okay, got about 15 minutes left. Let's do the last idea. The last idea is an idea that you guys have seen before already. It's power. You guys have seen power. This is the same definition of power given in electricity. Can be used here. Also measured in watts. Now, for those of you that didn't do, which is just, of course, Vince and Jason, this is the formula of power. Power is energy over time. It's how much energy you're expending over time. So when we look at this, we are going to be using, to calculate power, we're going to be going like mgh over t. How much, potential energy have we gained over time? We're going to go P equals half mv squared over time. How much energy is there? How much kinetic energy do we gain over a certain amount of time? And that will be that'll be linked to how fast that object is moving. How much. There is one interesting ramification of this though. If you do instead Fs, because that's work, remember work equals Fs. If you do work over time, that's the same as saying force times displacement over time. And displacement over time is velocity. And that gives you, that is actually an interesting formula. That is a new formula. This is the force applied at an average speed. So the examples that I've seen from textbooks that they give for these types of things is imagine that you're on and this is actually very, very similar to the questions that I used to give all the time. Let's just say you're on a bike and you're riding that bike at, we'll go with like 10 meters per second forward. And it's a constant 10 meters per second forward, which means there's no net force. Remember with these types of questions, right, that all of the laws we've learned about Newton's laws still apply. If you've got a constant speed, then that means there's no net force. Now, if there is no net force, you could say, well, what? And let's just say that it's being 100 newtons is acting on. Maybe we'll go with a different one. We'll go with 300 newtons is acting in friction. In order to make sure that this has no net force, he must be pedaling forwards with a force of 300 newtons. So then we could say, well, what's the power here? The power is 300 newton is equal to power equals to force times velocity. In this case, the force is 300 newtons times the velocity, which is 10 meters per second, which is 3,000 watts or 3 kilowatts. And so that's actually a way that we can look at how quickly that object is. And that can link to the average speed. You could also go backwards. You can say, oh, this is a force, this much power is being applied with this much force. What's the average speed of the moving object? Yeah, backtrack and calculate it out. If they were applying a greater force, then that would mean that there would be a greater speed. Let's do a basic question on power, and then I'm going to be pretty happy with how far we've gone. The basic question on power is this one here. And I like it because it's just nice and simple here. So calculate the power required to carry a box of 2 kilograms up a 5-meter staircase in 20 seconds. Now going up a staircase in 20 seconds shouldn't be too hard. You may have to pardon me, you may have to 20 seconds. It's not, it's actually a pretty long time. So it's not like you're sprinting up the stairs. But how much power are you using? What is the power rating that you need? So like the power in this case, and if you can think about it, right, if you were trying to carry, like, you've got a 2 kilogram mass here, but if you were trying to carry maybe 50 kilos, which is a really heavy dumbbell thing, you're trying to do that in like 10 seconds, that's going to require a lot of power. So you're going to have to be quite muscly to do that. This is not too intensive. We're going to see that now. Power equals energy over time. In this case, we're changing our gravitational potential energy. So it's going to be Eg over time. Now, Eg is our potential energy got to do with gravity, is going to be mgh. It's how much the mass times the gravity times the height. I found this really easy to remember, this formula, by the way, mgh, just because it's got my initials in it, mg, Macria, then h, but yeah, that doesn't help anyone else aside from me, so sorry. But yeah, you can maybe think, Mr. Greer, I don't know. So m, the mass is 2 kilos, times the height, which is times gravity, which is 9.8, times the height, which is 5, all over the time, which is 20 seconds. 2 times 9.8 times 5, all divided by 20. 4.9 watts. 4.9 watts, because remember, energy, power is measured in watts. Now, of course, if they were sprinting up the staircase and you was doing it in 10 seconds, that would be 9 watts. If the box weighed 20 kilos, then it would be more like 490 watts. I'm a bit lost. Maybe it would just be 49 watts. I think it would just be, yeah, it would be 10 times larger because the mass is 10 times more. But yeah, that's how much power needs to go into doing that amount of work in that amount of time. And that's the same sort of thing we talked about. That's the same sort of thing we talked about when we talked about energy and electricity. It was how much time do we have to do this work? In this case, we're doing 2 times, we've got 98 joules of work, but we're saying we're going to do that 98 joules of work over 20 seconds. But we could do that 98 joules of work over 30 seconds and 40 seconds if we took our time. And that'll figure out how much power we need. This is also very similar to the example that I had way back at the start with regards to the ramp and the staircase. It's very similar to that sort of thing there, in that you're like going, well, how am I going to share, how much power do I need if I do this over a certain amount of time, over a certain length, or stuff like that. Are there any questions on this? All right, ladies and gents, that brings us to the end of this topic. And the other part as well is this is the final exercise that I actually need to necessarily give you guys. And because I didn't want to, because I was like looking at it, I was like, oh my God, there's like 14 questions there. I thought, I don't think you guys need to do all those questions to get enough practice of it. Questions 1 to 3 are just some of the basic calculations, and 6 to 9 sort of start to make you think about it a little bit deeply. With question 14, just being one with a net force type question, like the one that I did at the very start, at halfway through with the bicycle. I think it's a good practice there, just to remind you guys, hey, you need to apply Newton's laws to these things. You can't just look at them in isolation. And then what I've got on the right here is I might start to do this with all of the lessons, but it's a bit late now. But I wrote down the 3 formulas that we learned today. The first one, which is the, and again, what I used to do is I used to create a formula sheet that I would have beside me, which was completely separate. I should let you guys know that for the test on Friday, I will let you guys have a one-sided cheat sheet, but I will provide you with a formula sheet as well. I'll have to make that, but the formula sheet will be electronic. But that's fine. It will be just like a regular sort of one, which will have all of the kinematic formulas, all of the motion formulas, all of the momentum formulas, all of the impulse formulas, the torque. But you'll still have to know stuff. So just because you've got all these formulas doesn't mean you'll know how to calculate net torque, making net torque equals 0. It's because you have all the formulas doesn't mean you'll know, what's the average force for this particular impulse. Yeah, but I would just like you guys to give 11.5 a try. And we're probably going to give you guys all of tomorrow to work on 11.4, 11.5, ask me some questions and so on and so forth. But ladies and gents, that's pretty much it for this lesson.